Are we ready to go?
Yeah.
Okay, well, I hope people can see me and hear me. I want to welcome you all to a Balliol online seminar. My name is Nick Trefethen. I'm the professor of numerical analysis in the Mathematical Institute and at Balliol. And this evening, we're going to hear a lecture by Ling Lin on symmetries in physics. And I want to welcome you all to what looks like a fascinating topic. Ling Lin is an early career fellow in the college. His official title is the Walker Early Career Fellow in Mathematical Physics. And he's a physicist and also a mathematician, and also a theoretical physicist. These distinctions mean a lot to those in the business. Ling grew up in Germany, in Heidelberg, and he did his studies there. He did an undergraduate 3-year degree, then spent a year at Cambridge, doing the legendary Part 3 degree in mathematics and physics at Cambridge. He went back to Heidelberg and did his master's and PhD. And then he was off for a couple of postdocs. He spent 3 years at Penn, the University of Pennsylvania, doing physics, and then another 3 years at the famous CERN Institute in Geneva, doing more physics. Came back here in 2022 to take up his positions at Oxford. So within the college, he has this very special early career fellowship. And within the department, the Mathematical Institute, he also has a very special position. He's called a Titchmarsh Fellow. And these are very rare. It's an extraordinary thing to be awarded one of these. So Ling is a young star of mathematical physics. He's also pretty good at some other things. Notably, he's a violin player. And maybe a month ago tomorrow, he and some other young fellows played in a concert, one of our Sunday evening concerts in Balliol, and they were wonderful, a Mendelssohn piano trio. So he's the perfect colleague, except for one thing, and that is that these high-flying young fellows are very employable. And I'm afraid that Ling has accepted a faculty position in Italy at the University of Bologna, which incredibly is 175 years older than Oxford, older than Balliol. So he'll be leaving us fairly soon this summer, unfortunately, to Bologna, but we are sure he will come back and visit often. Now, before we start, let me just mention a few things about how things work. Ling will speak for about 45 minutes. And during that time, we won't take questions at that time, but you're very welcome to type things into the Q&A box. So there should be a Q&A button at the bottom of your screen. By all means, raise some questions during the talk if you wish. And then afterwards, we'll have a question and answer discussion of maybe 20 minutes or so. And we can pick up questions from the Q&A box. And also at that time, of course, you can add further questions. So roughly 45 for the talk and then 20 or 25 for a discussion session. I guess that's all I need to say. So my phone is ringing. I will turn it off with apologies. Ling, on to you.
Thank you. Thank you very much for the introduction, Nick. And thanks everyone for being here. As Nick already mentioned, the subject of my talk will be about symmetries in physics. Which I think is a fascinating topic and which also motivates a lot of my current research. So I hope that within the next hour, 45 minutes, I can convince you that maybe share some of my excitements with you about the subject. So maybe to get started, since symmetries is maybe not something that the layperson has a concrete conception of what it means in physics, maybe I should start with a short description of what actually it means for theoretical physicists to try to understand the universe. So in fact, historically, what humans have done in order to understand our environment, nature, is that we create models of said aspects of nature. And these range from various levels of sophistication throughout history. For example, the Kepler model governing the motion of planets, a Big Bang in our more modern understanding of how the cosmos came about, standard model of particle physics that describe the elementary particles, and also Cooper pairs and Meissner effect in modeling what's known as a superconductor. But of course, these are models in the sense that they are concrete realizations, they're concrete instances of what physicists would call a theory or mathematical framework. And in some sense, you can think of these as really a set of language, a language with a set of rules, set of grammar that allows you to describe such models, that allow you to come up with descriptions of nature. And again, these mathematical frameworks, they undergo a change throughout history in terms of their sophistication, in terms of their applicability, in terms of their mathematical abstraction. And here are just a few of them that maybe are more familiar in throughout the popular literature. But of course, what is incredibly important is that in this line of work is that we try to really, in order to create better models of our universe, first and foremost, we need to make these frameworks work in a better way. And so to achieve that, these kind of progresses are driven by mathematical advances and also conceptual developments that not only enforce our ability to create better models, but also change our understanding of how these frameworks work, what's a better description at a fundamental level of nature, in order to make better models, more predictive models, or models with a wider range of applicability. And within these set of tools that improve this process, symmetries play a fundamental role. And this is what I'm trying to dive into momentarily. I should say, of course, that there is in fact also influence in the other direction, in that, and this is maybe more familiar to people thinking about how a physicist typically works, is that we conduct observations, we make experiments based on our models, and they will inform not only about what the model has to be improved on, but also what the underlying mathematical frameworks, these theories, may need to be modified into in order to make better models. And this line of work has worked extremely well for the last centuries, but actually, and this is a whole topic for another talk that I will not have much to say about today, but actually we're now sort of hitting in the history of maybe modern science, a point where all observations, experiments that are made are not going to tell us so many new things about our models anymore. So now comes a time where maybe we need to find different inputs that gives us new ideas about how to improve our models and how to improve our theories. And I'm just putting out, of course, something that is close to the work of a mathematical physicist, namely the set of mathematical consistency conditions, again, which is intimately related to symmetries in some sense, but also maybe more less popular amongst current working physicists, is that maybe also philosophical debates, thinking about asking what is a good question to be asking may be important. But again, as I said, this is not the subject of today, so I will return to my discussion of symmetries. So maybe we should start with just a brief introduction into a brief discussion about what are symmetries. And the word symmetries comes from ancient Greek, where it means roughly something like agreement in dimension, in proportion, and arrangement. And this kind of explanation agrees well with our daily intuition, where symmetry is oftentimes synonymous to beauty, to harmony, to balance. And of course, one of the most, I guess, intuitive notion of symmetries is that of a reflection symmetry, and by which we mean that a human face, roughly speaking, has a reflection symmetry from the left and across an axis separating the face into the left and right. And in fact, even though maybe not 100% accurate, there is a notion in which more symmetric faces, so where the left and right side of the face agree to more degree, are conceived as more beautiful, more harmonious. And likewise in other aspects of nature, for example, in the plant world, or also in our early conceptions of our solar system, these ideas have played these sort of intuitive idea of symmetry have played an important role. Now, as we move to a more concise definition of symmetries, it helps to point out how mathematicians think about symmetry. And they make that notion of what it means to be more symmetric or less symmetric very precise. And just as an example, I'm putting out here a circle compared to a rectangle compared to some irregular shape. And for a circle, you will immediately agree, I hope, that it looks the same no matter how much I rotate that circle, or no matter by how much of an angle I'm rotating that circle. But if I take that rectangle and rotate it, it will only look the same as this if I rotate it by 180 degrees. And furthermore, for an irregular shape like this, there is no amount of rotation I can do except for a whole 360 degree that maps it onto itself. So there's a very obvious sense in which a circle is more symmetric than a rectangle, which is more symmetric than some irregular shape. So in physics, this notion of invariance, so something that doesn't change under certain, in this instance, rotation, some change to its physical appearance. In physics, the invariance that we care about that constitutes the importance of symmetries is the invariance of physical laws. So, what do I mean by that? So, very simply speaking, imagine you have a laboratory where you are placing some experiment. In this example, it's some tabletop experiments with lasers. And the invariance of physical law means, for in this example, is that we can imagine rotating that setup with respect to the lab. And we should not be measuring any different results about, for example, what the specimen looks like. So there is a sense in which the rotation of this of our physical apparatus does not change our physical laws. And that's precisely what in the physical context is meant by symmetry. So symmetries arise already in a very prominent way in Newtonian mechanics, but there it is more thought of as a tool to facilitate a more explicit description of your model. And to elaborate on this a little bit more, let me just explain briefly how Newtonian mechanics works. And typically, this is maybe hopefully familiar to you from high school physics or just daily life, really, is that we think of most objects in nature sort of moving along a certain trajectory, certain line in space as time progresses. And this motion can be described by basically knowing the position of that object at a given time t. And if you know the position of an object, you also know its velocity and its acceleration. If you're familiar with calculus, these are just derivatives, but it doesn't really matter for what I'm trying to say. The point is that we are all very familiar with the concept that objects in daily life, they move or their motion changes due to forces acting on them, right? And Newton put it in a very concise formula, namely that the equation that governs this motion is a relation between the acceleration, so something to do with how the position changes of that object, and the external force F that acts on it. And typically this formula is written as F equals ma, but if you write it in ma equals F, then you get sort of an acronym for mother of all formula, which is why I had the slide title. And typically such a solution, the solution of such of the equation is typically very hard to determine in a most general setting. So in that sense, symmetry appears as a helpful tool, because if this external force, which governs the motion of this particle, exhibits certain symmetric properties, then mathematically speaking, the process of finding a solution that describes the motion of this object entirely is easier. So the example I want to look at is how the planets move around the sun, and that is related to a rotational symmetry of the force of gravity. And so the gravitational force has this formula. It doesn't, again, it's hopefully familiar to some of you from high school physics. What it means, roughly speaking, is that the force the sun exerts on the Earth is depends on its distance, the variable r, but its direction is always pointing towards the sun. And so there's a rotational symmetry in the sense that no matter how the Earth rotates around the sun, the force is always just going to be in a direction towards the sun, and it's just depending on the radius, on the distance, which of course doesn't change if I just rotate the Earth at a fixed distance around the sun. And it turns out, if you go through the math that we teach in first-year mechanics courses, that it's fairly simple to understand that this kind of symmetry has as a consequence that planets move within a plane around the sun. So by that, I mean, again, something that we're overly familiar with is that the Earth moves around, roughly speaking, a circle, but it doesn't sort of jiggle around as it encircles the sun, right? It moves around a circle, and there's a plane in which I can embed the circle. So in what sense does it simplify our description? Well, if you think about the original problem we had that Newton's equation tells us, we would be trying to find all three spatial coordinates in order to fully describe a moving object. But because of the symmetry principle, we know that it only moves in a plane. And in a plane, there are effectively only two unknown variables. For example, the radius or the distance from the sun and a certain angle that I can prescribe with respect to a certain chosen null position. So I'm already reducing the problem to solving three variables for solving only for two variables. And indeed, using this technology, Newton could show that the orbits of planets around the sun, or any celestial object around the sun, follow these shapes, which are called conic sections, and they match perfectly with what Kepler has previously found empirically in his Kepler's laws. So just to reiterate again in this example, in Newtonian mechanics, the dynamics is entirely determined by how the forces act on a certain object. And in order to find the corresponding, the resulting motion of the object, symmetries can help you to do that, to find such a solution more easily. And in the case of the Earth around the sun, again, we reduce the problem for solving for three unknown variables to only two unknown variables. But what's more is that because of this rotational symmetry, we can also generate new solutions, because in some sense, the Earth doesn't care really about whether it's rotating in this plane or say in another plane that I'm obtaining from applying a rotation to this plane in which the Earth moves. And in the jargon of the symmetry in physics, this map, this operation that I did in order to rotate the ecliptic plane into this different configuration, that's called a symmetry transformation. And symmetry transformations form what's known as a group in the context of mathematical structures. Now, I'm not going to go into details of group theory, etc. I just want to put it slightly in context, because group theory is a subject that mathematicians have studied since the early 19th century, and it's sort of been put spearheaded by Galois in order to solve problems around determining the solution of polynomial equations. And then Felix Klein realized that group theory can also play an important role to understand geometry. But its conceptual importance of symmetries beyond just a tool to solve equations more easily really came about with the work of Noether. So what Noether discovered is that for every symmetry transformation, there is something that is a conserved quantity. And by conserved quantity, we mean it does not change in time as the system is evolving due to the dynamics. And this idea of conservation actually holds beyond Newtonian physics. And it's a very, very important result that affects very modern developments, as I will highlight later on. So let's just go back to this example that we looked at with the planets. For a rotational symmetry that we discussed, the conserved quantity is the angular momentum. The angular momentum is the vector, so how can one visualize this? It turns out that this angular momentum vector is nothing but the vector that is perpendicular to this eclectic plane. So in some sense, the simplification of solving the problem of Earth moving around the sun inherently makes use of the angular momentum conservation, because if Earth was not moving in this plane and was jiggling around, then this angular momentum would be changing as Earth moves around. But because angular momentum is conserved and it's a vector perpendicular to the plane of motion, to the direction of motion, the Earth can only move in a plane. Something that may be more familiar again from day-to-day life is that momentum is a conserved quantity that we see, for example, if we kick a football and someone tries to catch it, or if a car hits a wall, then the damage that it causes is mostly due to momentum conservation. And that comes about because in the laws governing the motion of cars, spatial translation is a symmetry. So moving from one place, say in Oxford, to a lab in Cambridge, that translation does not change the physical laws. And similarly, energy conservation from Noether's work is actually related to the fact that time translation is a symmetry, meaning that physical laws remain the same whether I try to explore them 100 years ago or 100 years in the future. And at the level of Newtonian mechanics, these conservation laws coming from rotational symmetry, translation symmetries, are in some sense only an empirical observation. So, and the observation is that basically all these symmetries are present for systems where there are no external forces acting on them. Right? But in principle, as we've seen earlier, if the external force acting on a single object has some very complicated form, then by no means do these symmetries have to be respected in Newtonian physics. But somehow our everyday life and the fact that these quantities are conserved in many different experiments is saying that maybe there's something more fundamental. It's not just a coincidence of how the forces in nature look like that they're conserved. Maybe there's a deeper reason. And this is basically one of the grand insights of Einstein. So just to reiterate again, in Newtonian physics, symmetries are really a consequence of how the forces act, how the forces look like that act on moving objects, that drive the motion of objects. And it's model specific in the sense that I can imagine, I can write down, I can even in a lab set up using some external forces, a configuration where these symmetries are not present. But the universe as a whole seemed to respect these symmetries. So what Einstein instead proposed, though maybe historically it's not quite right, but sort of in hindsight, that's one way to phrase how Einstein what Einstein's idea is really saying, is that instead of trying to find symmetries given a set of physical laws, we should be putting symmetries in the forefront and derive laws of physics from them. Right. So, for example, in order to address the fact that the speed of light must be constant, which before Einstein was found in the famous Michelson-Moore experiment, what Einstein proposed is that there should be a new kind of rotation that mixes time and space, which is a symmetry. So instead of just rotating space within itself and leaving time invariant, there should be a rotation that changes both space and time at the same time. And it turns out, just by virtue of imposing this rotation to be a symmetry, all resulting models, no matter what you write down, must respect the fact that speed of light must be constant. And in fact, you can also think about what it means in such a symmetric world to be the conserved quantity associated with time translation. So what I've just said is that there's a symmetry that rotates between time and space, but of course, just translating along time is still a symmetry. And in this modified universe, well, it's not really a modified, it's actually our universe, the conserved quantity that Noether would compute for you according to a theorem is the energy which obeys this formula. So, and you recognize if an object has no momentum, so if it's resting, then you recover the famous E equals mc squared. Of course, what this formula is telling us is that as the object starts moving, the effective mass of that object, which contributes to the energy, will grow. Now, there's another insight that Einstein found, which goes by the name of the equivalence principle, which is roughly formulated as saying that gravitational force should be indistinguishable from force due to acceleration, meaning that if someone would conduct this famous experiment within a closed box on an Earth where he drops a basketball, that person would not find any difference for the motion of the basketball than in a rocket where the ball falls down due to the acceleration of the rocket in one direction. And in a slightly more symmetry-related language, this equivalence principle is saying that this change of reference frame should be thought of as a symmetry transformation. And the whole point is that if this change of reference frame is supposed to be obeyed by all kinds of experiment, all kinds of physical laws, then what Einstein showed is that in some sense, gravity has to be the curvature of space and time. There is no other way that such a symmetry principle can be respected by gravity. Okay, so let's just recap briefly what this change in perspective brought for us. So, as I said, in Newtonian physics, symmetries are consequences and of physical laws. And after Einstein, symmetries are now a much more fundamental property of theories, in the sense that their presence constrain the laws of physics and not the other way around, as was previously described for Newtonian dynamics. And specifically the symmetries of space and time, which puts them onto the same footing and therefore creates the notion of a space-time, that was essential for Einstein to develop his theories of special and general relativity, two theories which now we use in many, many different models that have hugely important impact on our day-to-day life. For example, most famously, maybe our navigation GPS system. And more interestingly, if you combine these, so far we have not talked about the quantum world, but if you combine these symmetries of space-time with quantum mechanics, you find that there's a new type of particles emerging, which are called fermions, which do not exist in the classical setting, even in special and general relativity, due to their weird nature somehow that, unlike ordinary particles which are called bosons, these fermions have to be rotated by 720 degrees, so twice around their axis, to appear as their original self again. Again, there's some beautiful mathematics behind why this appears once I combine symmetries with quantum mechanics, but for the sake of time, let's move on into other symmetries that the quantum world possesses. And this is really the place where the importance of symmetries shine. So concretely, what I'm going to talk about now are symmetries at subatomic scale, symmetries that govern the interactions and the properties of elementary particles. And first of all, I should say that the correct mathematical framework, the theory that we have to use in order to describe these things, are called quantum field theory. And within quantum field theory, we managed to come up with one of the models of our universe, or at least a part of our universe that pertains to these elementary particles, which is called the standard model of elementary particles. So in that model, you have a bunch of elementary objects which give rise to these particles that you maybe have seen in one way or another in some popular science books. They're roughly divided into matter particles and force interaction or force carriers, and in some sense, in a very precise sense, this model of nature, of an aspect of nature, is really the most accurate model that humans have come up with. Most accurate meaning that it agrees with all experiments we have been conducting so far with amazing precision. Now, I won't have time to explain what quantum field theory is and how these particles come up within this context. Instead, what I'm going to focus on is the notion of a gauge symmetry, which really is at the core of the mathematical formulation of the standard model. And the name, actually, the how gauge symmetry, or what gauge symmetry means, is hidden in its name. Namely, the word gauge means that in a more pictorial way speaking, it's a device, for example, a ruler or some other measurement apparatus that you use to encode some information, right? So it's really an external object. I wouldn't want to call it external. It's an arbitrarily made up object that is simply there to capture some features. In this case, it captures certain features of these elementary matter particles. For example, their charges, their color under the strong interaction, etc. And just like as a ruler, you could imagine changing your markings on the ruler when you are encoding this information. And the word symmetry in the name gauge symmetry means that the physical outcomes cannot possibly depend on how you choose to mark your ruler, right? What you call a centimeter, what you call a meter, are just arbitrarily made up quantities that should not matter for the size of, say, a table that you're measuring. So in that sense, gauge symmetry, in that sense, that's the meaning, the sense in which measuring something with a ruler constitutes a gauge symmetry. Now, being another way to phrase this fact that the physical outcome cannot depend on it is to say that two descriptions of some mathematical descriptions of a physical system that are related by a gauge transformation. So by changing your markings on a ruler, they must be physically identical. And in order to to exchange your information that you have measured using a certain gauge, you have to basically pass on that gauge to, or the information encoded in a gauge, to someone else in order to exchange information. And in this particle physics world, you can think of these gauge bosons as precisely this artificial object that you use to measure properties of these matter contents. And for these matter particles to interact with each other, they have to exchange information about themselves using a gauge. That is to say that they particle interactions are mediated, are transported, are generated in some sense by these gauge bosons, by these gauge particles. Now, this is a very, very crude description of what gauge symmetry is, and I hope you appreciate that there's much more deeper mathematics and physics behind it, which I cannot. I don't know how to. I'm not able to explain in this short time. But it also means that this pictorial description has many limitations, and you should not take it too literally. And one further comment that I want to make about gauge symmetry is actually the fact that gauge symmetry is in some sense also geometry. And I make this comment because oftentimes it's said that the reason why gravity is so different from the other elementary particle forces is that gravity is related to geometry of space-time, whereas the other forces are not. But in fact, it's not quite accurate. And if we think about it slightly more, it turns out that both are very similar to each other. If you recall from earlier when I said that gravity should be indistinguishable from being accelerated, it means that this change from a rest frame with gravity to an accelerated frame without gravity, this change, this symmetry transformation is actually a gauge symmetry based on what I just said, right? This transformation should not make any impact on the physical outcome of any process. So in that sense, general relativity is a gauge theory. And something that is unfortunately, again, much harder to explain without delving into the math is that gauge symmetry, at least in a classical setting without adding the quantumness of the nature, is also a kind of geometry. More precisely, what we think of the electromagnetic field, for example, it is describing the curvature not of space-time, but of some auxiliary space that we cook up to. But within this auxiliary space, the electromagnetic field, and by extension also the other fields describing the strong and weak interactions, can be thought of as describing a curvature. And the motion of electrons in such a background field can be, in some sense, thought of as straight lines dictated by the curvature of this auxiliary space. So really the difference between gravity and gauge boson is not that one is geometry and the other is not. It's more related to the fact that gravitons, the elementary particles of gravity, if you would promote Einstein's theory to naively to a quantum theory, has spin 2 rather than spin 1 as the other gauge bosons. This is again a very subtle mathematical distinction that just using words it's hard to explain. But it turns out that because of this distinction, that's really where the mathematical problems arise when we try to talk about a quantum theory of gravity. And that's why quantum gravity is hard, because we don't know, unlike for the gauge bosons, the photons, the gluons, which have spin 1, we don't know how to make sense of them quantum mechanically for spin 2 particles. But this is another subject that I will not touch upon more. Let's go back to symmetries, and importantly to symmetries in the elementary particle world. So far I have tried to advertise how symmetries mean some kind of invariance, which is responsible, which is encoding all this interesting structure. But actually, it turns out that in the quantum world, symmetries are even more interesting and even more powerful when we think about them as being broken. So what does it mean to be broken? It means that it's not that the underlying physical laws do not respect that symmetry. It's more that a particular state in which the physical system is in violates that symmetry. So let me explain it using one of the most basic examples, namely that of a magnet. And we're all familiar with, hopefully, with the idea that if we think of the magnet really as built out of, say, little iron atoms, then each iron atom has a magnetization, constitutes a tiny elementary magnet. And if I have if I place such a magnet in a very high temperature, then the tiny vibrations of the atoms due to the high temperature will result in a configuration that where all the individual elementary particles point in random directions. So at a coarse-grained level, if I look at this magnet from far away without seeing the magnets, I would say that there is no preferred direction. So there is in some sense a rotational symmetry. There is no magnetic field, no preferred magnetization in that magnet, and that high energy phase of the magnet that respects the rotational symmetry. But if I cool down the magnet in an or just get a magnet you can buy in supermarket, then what you find is that all of the elementary particles are aligned with each other, and they create a overall magnetic field that singles out one direction. And of course, if I would rotate this magnet, then it's not invariant. The magnetic field will point into another direction. That's not to say that the underlying rotational symmetry that Einstein has taught us about in space-time is broken. It's just saying that that particular object, the magnet, in its current state, has broken the symmetry. And this idea of symmetry breaking due to certain configurations of the system rather than the laws of the system governing the dynamics of the system, that in condensed matter physics has been utilized greatly to describe phases of matter. Phases of matter, for example, as we just talked about, for a magnet that has a overall magnetization versus one where it doesn't. But also you can use these ideas of symmetry breaking, for example, to study more sophisticated phenomena such as superconductors. And in fact, this very same mathematical framework of symmetry breaking is what's responsible in the Standard Model for the mass acquirement of elementary particles through the Higgs mechanism. And very roughly speaking, the symmetry that is broken here is the fact that if I sit at this point, I would perceive this so-called Mexican hat to be rotational symmetric. But if I would go into the valley of this hat, then I can no longer rotate around myself without seeing any difference. And I should just say one word about this Higgs mechanism / symmetry breaking is that in the Standard Model, this is the reason why, for example, the Z and W bosons acquire mass, unlike the photon and gluons. And in some sense, because we knew for a long time about the symmetries of the W and Z boson, but haven't found the Higgs in the lab, because of the mathematical consistencies surrounding gauge symmetries and how they are broken, we knew before building the LHC at CERN that even without the Higgs particle as such, the detector will find something new, just based on mathematical consistency of the gauge symmetries for these weak force bosons. And that led physicists to say with confidence that we should be spending billions and billions of dollars, even though there were no prior, not much prior direct evidence for the fact that there is even a Higgs boson. Okay, so let me move now to really the more modern notions of symmetries beyond the 20th century. So we have seen many types of symmetries related to space-time rotation, space-time transformations, and also symmetries called gauge symmetries at the level of particles. But there are also many more exotic type of symmetries. For example, you may have heard of supersymmetry, less known things called duality transformations or higher spin symmetries, And these are all type of symmetries that are currently really reshaping and help advancing our understanding, our mathematical understanding of our theories. And I should point out that this is not to say that symmetries, or said differently, this is not to say that symmetries necessarily need to have an impact on models. Of course, they will have, but it's also important to note that, for example, even though we haven't found supersymmetry as a symmetry of nature in our current experiments, there's nothing valuable about the concept of symmetry in our advancement of our theoretical framework. And in fact, there is a more recent generalization that of symmetries. And this has to do with, if you remember from earlier, the notion, the work of Noether, where she showed that symmetries give rise to conserved quantities, angular momentum, energy, momenta, etc. But this new idea of generalizing the notion of symmetries reverses this logic. In the new notion of generalized symmetries, we don't think of conserved quantities as a consequence of symmetry. Rather, we should be thinking of conserved quantities as the reason for there to be a symmetry. And this is a very, as I said, very recent notion of symmetries that was just put forward, really formalized about 10 years ago. And it's a highly active field of research that I'm also interested in. And roughly speaking, the change are twofold for these kind of symmetry. One is that unlike previous symmetry that we talked about, where we typically think of them as in the world of point particles, they really describe some modifications of a point-like particle. These generalized notions of symmetries can now be applied to extended objects. For example, a line of charges or a surface charge. And maybe some of the more mathematically inclined audience, what this type of symmetry actually is telling us is that we no longer need to restrict ourselves to the mathematical structure of groups when we talk about symmetry. And in fact, this notion of symmetries has arisen previously in different ways in condensed matter physics. And through this more formalized notion, it has provided it has provided a wealth of new ideas flooding from one area of physics into the other, mostly between condensed matter physics and high energy physics. And I should say this last part about the abandoning of mathematical structure from groups to more abstract objects opens new doors for collaboration and exchange with much more formal, what previously thought much more formal aspect of mathematics, namely category theory. Okay, so with that, let me come to the conclusions. So I hope I have provided some evidence, some explanation to why symmetries are really important objects in to propel our understanding of the universe. They start out as certain invariants of physical laws under change of description, but really what they've become over the last 100 years or so are really guiding principles that help us come up with new ways of writing down mathematically consistent physical laws that describe the more intricate aspect of nature. And in this new notion of generalized symmetries, what we find is actually many different phenomena across different areas of physics, which previously were described in one way or another, but not in the language of physics, of symmetries, now have a natural unified description in the notion, using this generalized notion of symmetry. And of course, there are questions about, many people would probably think that what are these symmetries good for in actual nature, whether or not they're making some new predictions. And currently, we're still working on that, working out precisely that aspect, namely what kind of interesting consequences there may be due to these symmetries in laboratory settings that we could detect. But what is safe to say is that these symmetries really provide a conceptual advancement in order to tackle some more difficult problems in theoretical physics, most prominently the unification of quantum physics and gravity, which I hope that, which is some of the parts of my work where I'm trying to see if these kind of symmetries may play a role in coming up with a good description of quantum gravity. And with that, I'm at the end of my talk. Thank you for your attention.
Thank you very much, Ling. I hope I'm visible. That was a fascinating talk, and I always like the historical side of things, and it intrigues me how you can interpret Newton through symmetry, though he probably didn't, but then Einstein did explicitly, and then the Standard Model even more so, and the 21st century even more so. So I love the sense of symmetry becoming more and more central to the way physicists think. Now, what we're going to do now, we'll have some questions and discussion. And so please, anyone who would like to raise a point, find the Q&A button at the bottom of your screen and put something into it. I will begin with a question or two of my own, perhaps. But before that, I wanted to alert people about the next one of these lectures on a totally different area. 4 weeks from today, the next online lecture is by Catherine Marshall. That's on the 11th of July. And Catherine Marshall will be speaking on, I've got her title here, what is political deference and can it help to repair the British Constitution? So 4 weeks from today. But anyway, back to physics. Ling, let me ask a question that maybe you touched upon in your final sentence, and I mean that literally. Of course, this isn't a technical talk, but I couldn't help noticing that you really didn't mention yourself. And what I'd like to ask is, does your work have a special significance, a special connection with symmetry? Or are you describing something that's universal and you're merely wrapped up in that? Or have you yourself been particularly engaged with questions related to symmetry?
Yeah, thank you. Thank you, Nick, for that's a good question. So I think for most part of the talk, given the sort of general audience here, what I've described is really work that has been done in the past, and it's sort of a huge area of research that I find fascinating. My current research is really focused on this, what I mentioned in the end about the generalized notion of symmetries, and specifically, I'm sort of interested in certain connections to quantum field theories that you cannot describe using, let's say, conventional methods, which are taught in sort of undergrad quantum physics. And it has to do a lot with our understanding quantum dynamics coming from works on string theory, which is part of my background work. But in part, what I'm trying to maybe elaborate more on and in my work and try to establish connection is that how insights from string theory can be applied to these kind of symmetries without referring explicitly to a constructive method of string theory. These should be concepts that are independent of string theory.
Yeah. Okay. A question has appeared on the Q&A that actually I too was wondering about. Many of us older people are very familiar with group theory as the classical way to study symmetry. And of course, physicists have been using group theory for many years. But at the end, you mentioned category theory, which many of us old-time mathematicians think of as what it used to be called abstract nonsense when I was your age. So we would like to know, tell us a little more about what's going on. What is category theory, if you can say a word about it, and how might that help out physics?
Yes, I can give my best, though I'm not sure I will succeed. So category theory, in some sense, is putting at the center the idea that objects are not intrinsically defined as by just properties amongst itself, but really through relations to other similar objects, right? So by saying that is, for example, the fact that a vector space is a vector space, something that is a group is not really anything to do with that set by itself, but it's really related to how I can identify, I can relate as one group to another and a third one, and how this sort of concatenation of relations are telling me about their internal structures. And this doesn't help you at all with, I guess, symmetries. But what the subtle thing about symmetries at the level of group theory is that, if you wish, you can also think about the symmetry action, right? Not really as acting on your physical setting, but they form this abstract group that you study through group theory. You can make sense of talking about a group abstractly without thinking of it as a set of transformations acting on the concrete physical system. And so when you study these generalized symmetries, you realize that, well, if you apply the same logic to construct an abstract set of these symmetry, these these conserved quantities, I should say, which I was saying that gave rise to these generalized symmetries, you quickly find that the set of groups is only a subset of the possibility that these charged quantities encode. So we've learned earlier, Noether told us that conserved symmetry gives rise to a conserved quantity. There's a really concrete sense already known in the early 20th century that these conserved quantities generate symmetry transformation at the mathematical level. But you can loosen the structure such a conserved quantity can have in order to do something to your physical system. And it turns out that these kind of transformations are more appropriately described by category theory. Fascinating.
Let me ask a totally different question, which you sort of skirted a couple of times, but also maybe mentioned right at the beginning of your talk. You mentioned that it's harder and harder to do experiments that are relevant to the fundamental laws of physics. And you even almost seem to hint that maybe in the future experiments will cease to matter and physics will be decoupled from that. Can you tell us more about that point of view and what your thoughts are?
Yeah, I can try without, maybe I'm going to say something very controversial there. But it is certainly as I was saying, the standard model is the most accurate model we have of nature. It also means that whatever new experiments we are trying to build, we're not going to learn something previously unknown about nature, because everything is already predicted by this fascinatingly accurate model. Likewise, Einstein's theory coupled to some cosmological fields describe very well to high accuracy what we can observe in telescopes in the microwave background about the expansion of the universe, etc. So there is, in some sense, this technological hurdle in that what we currently build in a lab just doesn't go beyond the limit of these predictions. That's not to say that these are the final models of our universe, because we know, based again on mathematical structures, one being the connection of gravity with quantum physics and how they are incompatible at some level, we know that these cannot possibly be the fundamental descriptions of nature. But the experiment you would have to conduct to explore phenomena related to this incompatibility are far beyond what we can achieve currently.
Yeah.
So by that, I mean, we need some other insight that tell us how to improve our theories, because within sort of this height of quantum field theory and particle physics, there in the 60s, 70s, a lot of particle accelerators keep feeding us data that told us how to improve our theoretical framework. that's, for example, underpinning the importance of gauge symmetries that I was alluding to over other types of interactions between particles. But we sort of hit a dead end with this, and now we need new types of insights. For me personally, string theory provides one, which is not to say that I believe string theory is a description of a universe, but I think it's pointing us towards some more intricate structures that we need to understand better if we want to facilitate a description of quantum gravity.
Yeah, okay. There's a question John McNamara has raised. So I guess you talked about fermions and bosons and spin and so on. And he's asking, can you say a bit more about why spin 2 is difficult to incorporate in quantum mechanics?
Yeah, so it's not just spin 2 by itself. It's more the fact that spin 2 as a gauge boson. And how should I say this? So it ultimately boils down to the mathematical details, but in rough sentences, the fact the type of interactions a spin 2 particle can have with itself is different than the type of interactions that a spin 1 particle can have, say the photon or the gluons, etc. And this slight difference leads to the complications when you try to, make sense of certain calculations which give you infinity. We know how to deal with these infinities if they come from interactions of spin 1 particles, but we don't know how to deal with these infinities if they come from interactions of spin 2 particles.
Wonderful. That's very interesting. Okay. There's a question from Dylan Baer. So I think he's making a distinction between fundamental string theory sorts of phenomena and condensed matter physics, which is a little more 20th century. So he's asking whether these generalized symmetries going beyond group theory can help us with condensed matter physics.
Oh, yeah. So maybe I should have said this more clearly in the talk, but a lot of the idea about generalized symmetries, before really formulating them in the language of symmetries, has come from the condensed matter community. So this idea of, for example, that I was alluding to earlier about phases of matter, magnetic versus ferromagnetic versus paramagnetic, superconducting versus non-superconducting, there are much more subtle distinctions of phases of matter in let's say systems you can explicitly construct in a lab. For example, topological insulators, which may ring a bell with some of you. But it turns out that some of these phases people have studied in these more exotic type of matter can actually be understood as these type of generalized symmetries and how they are broken, for example.
Yeah.
Likewise, there is a kind of specifically non-group-like symmetry that, for example, relates in a simplified model of magnets called the Ising model. It relates the phase, which is disordered at high temperature, where there's no preferred alignment amongst neighboring magnets, and the phase at low temperature, where just due to the interactions between different neighboring magnets, everything points in the same way. And you would say, okay, these two systems obviously look very different. But if you study a bit more carefully the mathematics describing these two systems, or these two states of the system, I should rather say, then you find there is a transformation that relates one to the other and tells you exactly all the things you want to compute in the other thing, which you can think of as a symmetry transformation.
Yeah. Huh. Okay. So I guess the things that one teaches one's students are changing with the decades. I don't know to what extent what you're saying is a little bit controversial or the universal opinion, but certainly you are recommending that more and more advanced ideas be used by physicists all the time.
I definitely advocate that, yes.
Okay. There's a question by David Blue. who raises the question of what happens when a system has several symmetries, more than one symmetry. And so suppose you have two symmetries. Is there a relationship between them? Is there some kind of symmetry that can relate one symmetry to another?
Very good, very good. So there are several layers, several different levels of complexity to how different two separate symmetries can be intertwined, right? In the most basic one, we said earlier about, say, the symmetries of space and time. You have rotation symmetry that gives rise to angular momentum conservation. You have translation symmetry that gives rise to energy and momentum conservation. Of course, there is, in some sense, these symmetries talk to each other, right? If I perform or let's say differently, what in this specific instance, translation in time and space and rotation in space all come together to form a bigger symmetry group, which is in the pre-Einstein world is called the Galilean symmetry. Post-Einstein, it's called the Poincaré symmetry. So you could indeed, at this basic level, separate a big symmetry group that has loads of different elements, different kind of transformations you can do into subsectors, and you can give them names. Yeah. So in some sense, this is the most basic, most trivial way two different symmetries can mix.
So would that mean for, oh, sorry, go on.
So no, go ahead.
Would that mean, for example, that instead of talking about translation and rotation, I could pick two other symmetries that, as it were, span the same space as those two? Yes,
absolutely, absolutely. Yeah. Or that's different. That's just another way to say that if you combine a translation and a rotation, yeah, the combination is also a symmetry transformation, right? That's maybe you will recognize, of course, that this gives rise to the group. But as I was saying to this other object about generalized symmetry, is that once you allow yourself to have these new notions of symmetry, there is a real sense in which you get a new type of mixing between these symmetries. And in some sense, that kind of mixing is related to the fact that you abandon the structure of a group, because you may end up with, after concatenating two different types of symmetry transformations, with a state that you cannot invert, for example. So you lose this fundamental invertibility in groups, and that's why sometimes these things are called non-invertible symmetry.
And this would be a point of view that would be widely accepted among physicists, or?
This is one of the views that have only been crystallizing in the last few years. So depending on who you ask, they may or may not have heard about these things as symmetry.
Yes, I see.
But as I said, in the context of condensed matter, there have been examples, where people have using these without giving them the names of symmetry.
Yeah, wonderful. Let's see, I think there's no more questions in the chat line. I'll give a moment if anybody wants to raise anything. By the way, I wanted to mention, I forget if you and I have discussed this, that there's a book by Doug Stone about Einstein, which I loved reading, and regarding Bose and all that. He pointed out that Einstein, in a succession of events in his life, seemed to understand the work of others more deeply than they themselves. And one of them was Bose. And so Bose did this work, and then Einstein saw the symmetries behind it. So the Bose-Einstein work was really Einstein's deeper understanding of Bose. And it does sound as if physics these days is obsessively looking just to go deeper and deeper in how it understands things.
I certainly agree, and that's not to say there are not physics research that is really dealing with just known phenomena and trying to come up with better descriptions of those, or I mean, most famously, the new development of quantum information. There's not something fundamentally new to that. The most of the physics that goes into that is early 20th century quantum mechanics, right? So there are.
If I were to ask, say in the last 10 years, has there been any discovery from the lab, as it were, or from the cosmos, maybe I should say, that sort of stands out in your mind as the biggest new thing that needs to be explained?
I mean, again, it depends on what you mean by explain, I would say. So you can, there's one sense of explanation in which you come up with a better model, with a more accurate model, or with a new model within the framework of what you're using that, for example, takes care of these new measurements. One of the famous ones, late 20th century, was the discovery that the universe is expanding. So this led to the idea of the cosmological constant. Well, not the idea, but really the popularization of the idea of cosmological constant that Einstein introduced way back in his time, and also dark energy, etc. I would say that in some sense, that particular example, you can, if you wanted to, use quantum field theory and model it perfectly well. It's just one parameter you have to add to your equation. Of course, there are then other deeper questions that adding such a term raises. And you may be inclined to say, well, are these questions answered by the models you have? And I would say they are not. But then again, depending on who you ask, they may not think of that as an important question. And that's why I mentioned this in the beginning. It's like we're now at a stage where maybe, you know, ideas in philosophy, ideas about what's a good question to be asking, what's a bad question to be asking, what's a, you know, worth answering, trying to attempt finding a framework, is there, what's not, really becomes more and more important. And so from that aspect, I don't remember any experimental finding that would warrant really a fundamentally new development of a framework, except for the ones that we know about that at the mathematical level, quantum physics and gravity are incompatible.
Yeah. We're going to miss you in Balliol, where we have physicists and philosophers Indeed. Of physics. Maybe we should have a final question. And so this, I guess, will be our last topic. Brian Foster, who is a professor of particle physics, recently retired, whom you know well. Like you, Brian, and like Einstein, the three of you are all violinists. And Brian is asking, do you see any connection between that side of you, your musical side, and your research, and specifically about symmetry issues?
It would be tempting to say yes, but if there is, then it's certainly a connection that I'm not, what's the right word, mindful of consciously. Maybe through dealing with the harmonies in music, I'm somehow more inclined to think about these kind of concepts. Yeah. But yeah, who knows?
So, of course, I'm a mathematician also, though not a physicist, and I like music also, though I'm not as good as you. But one thing one gets, one hears a lot is, what do you think of the connection between mathematics and music? And I know I've found over the years that I don't have anything very interesting to say in response to that. It seems to be there, but I don't know. We live it, we don't understand it. Yeah. Ling, this has been absolutely fascinating.
Thank you.
I'm sure the others share my view. Oh dear, some anonymous person is trying to ask another question.
Oh yeah. Yeah, should I answer? I think, yeah, I'm maybe somehow inclined to give a brief answer.
We'll have one more question, but after this we will stop. So the question that's just appeared is a philosophical question. And is the physical world so complex, or, of course, we all want to know the answer to this, will it all in the end boil down to one simple theory of everything? Of course, nobody knows the answer, but we'd like to know your opinion.
Yes, exactly. So as you said, the answer, of course, right now is absolutely unclear. The thing I wanted to respond to in this question is actually precisely a notion that is related to these symmetries in some sense, but more string theory has taught us, is that there may not be a absolute way of saying what's complex and what's simple. There's not a absolute notion of what's a easy description, what's a complex description, and what's a straightforward description. In fact, through string theory, there have been, and by now it's sort of gone beyond string theory, there are various type systems described, for example, both one described within gravity, one doesn't have gravity, and they turn out to be, in some sense, in a very concrete sense, physically equivalent. But what seems complicated on one side becomes, if you understand the dictionary, very simple on the one other side, and vice versa. So,
okay,
yeah.
I'm not sure you taken a firm stand there.
No,
okay.
yeah.
Okay, well, you'll let us know. On behalf of all of us, Ling, thank you so much. It's been a wonderful hour. Thank you so much, and goodbye to everybody.
Bye, everyone.